So I just wanted to quickly finish off what we were talking about last time, and that's the symmetries of the Dirac-Lagrangian. And we talked about the global U1 symmetry, which leads to this vector 4 current. And today we'll see that this can be interpreted as electric charge current. So here it's important to note that alpha, the parameter transforming, is a constant. It's not a function of space-time. Such symmetries are called global symmetries. In a couple of lectures, we will come across what are known as local symmetries or gauge symmetries. And I'll argue that that's actually a misnomer in the sense that it's not actually a symmetry of your theory rather than a redundancy of description. However, coming back to global symmetries, in the limit where the mass term, we set the mass term of the Dirac-Lagrangian to 0, we have another additional symmetry, which probably shouldn't surprise you. It's the chiral symmetry, where psi goes to e to the power I alpha gamma 5, so you're exponentiating the gamma 5. And if you think about it a little bit, you'll see that this implies, if we think of psi bar as psi dagger multiplied by gamma 0, that this should transform like so, right? And then the kinetic term of the Dirac-Lagrangian remains invariant. Yes? No. No.
No?
Because gamma 5 anti-commutes with gamma 0. So when you take the Hermitian conjugate of that, okay, let's see. So psi goes to e to the power I, gamma 5 alpha of psi, right? So psi dagger goes like this. There's a minus sign here. Now, if you expand this out, the terms which has even powers of alpha, there the gamma 5 squares to 1, right? So those terms do not have gamma 5. The odd power of alpha, they have only one single gamma 5. So now, then, if you multiply this relationship with gamma 0, and you commute this through here, the terms with the even power of alpha do not pick up a sign. The terms with the odd power alpha picks up a minus sign, right? And therefore, you can write this as. Okay? So this is an example of a symmetry which the quantum theory breaks, and by something called anomalies, which unfortunately we shall not have time to investigate in this course. Yes?
I have a question about the gamma matrices. Notice that you always write gamma 5 with the 5 down. Is there a reason for that? Like it's not something that we
I define gamma 5 in a particular way. Now, if I go to a 5-dimensional space-time, I might, with a Minkowski metric, I'll have to raise the index of gamma 5. Then, I'll pick up a minus sign for the gamma 5 upstairs.
If we were in a 5-dimensional.
Yeah, it doesn't really matter, right? For this purpose course, for example, in the tutorial last week, we actually defined gamma 5 with a minus sign, but the 5 was upstairs. So that's kind of a convention, but yeah, it's not very important for this.
Can the mu on gamma mu be raised and lowered? Or?
Yeah, of course, gamma mu can be raised and lowered by using eta. It's completely consistent with the properties of gamma matrices are completely consistent with raising and lowering. But gamma 5 is not really a space-time. It doesn't have a space-time index, right? So, okay. Okay, and then we have our good old translational symmetry. That is, if you take our system and move it 5 meters this way or 5 hours in the future, at least the fundamental Lagrangian should not change. And that leads to the conservation of the energy momentum tensor. Note that you can always add stuff to the energy momentum tensor which vanishes on shell. And you can use that to actually, so for example, in GR you saw, did you see a definition of a energy momentum tensor in GR? So that, the definition was something like, right? So, oh my God, something smells good. But that definition was symmetric. Whereas you see here, the definition that we use in field theory, which comes from Noether's theorem, is not necessarily symmetric. But you can actually add stuff to the energy moment tensor which vanishes on shell. And then you can, it's, what I'm trying to say, it's not unique. You can, in fact, this expression for the energy momentum tensor is, I've used the equation of motion to write this form. The conservation of the energy momentum tensor always uses the equation of motion. Okay. And lastly, and not least, the invariance on the Lorentz transformation. It's kind of a long calculation, but you know it's worth doing. Now, there is this part which is the usual angular momentum bit that we had in a scalar field theory. So this you can, the spatial components, the ij components of this, you can interpret as the angular momentum of your spinor field. The 0I components have the interpretation of the center of mass of your system. Whereas this term, this bit is the new one, and that's just the spin part of your angular moment, total angular momentum. Okay? All right. So that today we'll talk about quantization of spinors. So far, I've only talked about classical properties of spinors. In the last class, we saw how to construct invariance of spinors and how to write down Lagrangians for spinors. And we came across two kinds of spinors and their Lagrangians. Well, three kinds of spinors, Dirac, Weil, and Majorana, but we wrote down the actions for only two of them. The Dirac one, which had a kinetic term and a mass term. The Weil spinor had only kinetic terms. We saw that the Dirac mass term, when we expressed it in terms of left-handed and right-handed spinors, was not Lorentz invariant, each individual term, right? Well, we had to include left-handed and right-handed. Each term included both a left-handed and a right-handed. Therefore, we could not write a mass term exclusively for a left-handed spinor. So, however, so Weil spinors also have this symmetry, the Lagrangian, you'll see. And in your homework, you'll work out the action for Majorana spinors, and you'll see that there are important differences in the symmetries of the Majorana spinor and the Weil and the Dirac spinor. Okay. So any lecture that talks about the quantization of spinors starts with a little bit of a waffle about spin and statistics. You've already done a tutorial on how the spin statistics theorem applies to the bosonic case. For the rest of the week, I'm going to talk about the spin statistics theorem for the fermionic case. I'm joking. I'm not going to do that. So I will not actually kind of go into the proof of the spin statistics theorem for fermions, but the fact that the spin statistics theorem is at the heart of the quantization process, I'll just point out here and there where that kind of comes about, okay? So Yeah. No. If you want to read the theorem, look it up. I'll give you a reference. It doesn't have the theorem per se, but it talks about all the different aspects in great detail, which is very, and from a very physical point of view. And the reference is, it's a really nice book, and it just came out, I think, earlier this year or last year. SM stands for standard model, in case you're wondering. Okay. So what does the spin statistics theorem tell us? So it says that in 3 plus 1 dimensional space-time, integer spin fields satisfy canonical commutation relationships, that is, they are described by Bose statistics, whereas half-integer spin fields satisfy canonical anti-commutation relationships. Therefore, they satisfy Fermi statistics. If you go one dimension down, if you go to 2 plus 1 dimensions, there is the possibility of having more general commutation relationships, not just commutation or anti-commutation relationships. And such particles, I think they were predicted before they were discovered. They're called anyons because they can have any statistics, I guess, is the word. So in effect, in 2 plus 1 dimensional condensed matter systems, people have actually observed effective particles. They are, of course, not fundamental particles, which have anyonic statistics. Okay. But we are not in this course, we are not going to cover that. So some comments are in order about how do we understand this spin statistics theorem. So comment number one is that you can prove the spin statistics theorem from the Lorentz invariance of the S matrix. So remember that the LSZ theorem tells us that these things can be computed in terms of the time-ordered product of a string of quantum fields it turns out when the time-ordered product involves bosonic fields, the Lorentz invariance of the time ordering operator implies that the bosonic fields have to satisfy commutation relationships. And, sorry, not bosonic, I should say integer spin. And if the string of operators involve half-integer spin operators, then the Lorentz invariance of the time-ordered product implies that they have to be they have to satisfy anti-commutation relationships. Okay, so this might sound very cryptic right now, but later today in the lecture, I'll point out where this comes from. This is actually closely related to the second way of looking at this theorem, which is from causality. So Dan told you that, but what we mean by causality in quantum field theory is that if we have some observable, in quantum field theory, an observable is really like it's a polynomial in fields usually, although there can be more complicated observables, but those are the simplest ones. Then the commutator of these two observables have to vanish outside the light cone. So if the I always write my two should be like that. So if the 2 points are space-like separated, which is what this means, then their commutator better vanish. Right? So what this means is that here is a cartoon diagram. This is x. So if x is this point and this point is y, you can't really send a signal from x to y if y lies outside the light cone of x. However, this thing should not vanish if y is inside the light cone, right? Or if it's even in the backward light cone. And lastly, and this is actually very important, I think, another way of thinking about the spin statistics theorem is via stability. Okay, before I go into stability, let me just kind of tell you a little bit more about how this comes about. The thing is that when you got spinners, spinners are usually made out of bilinear. Observables of spinners are made out of bilinears. So if you have so observables in, say, a Dirac theory will have some form like this, where this is some element of the Clifford algebra. By Clifford algebra, what I mean is that various combination of the gamma matrices, say antisymmetric combination of the gamma matrices, the whole set is called a Clifford algebra. So given this form of the observable, you can expand a commutation relationships in terms of either like commutators of size or anti-commutators of psi, right? It's by choosing that the commutators of psi, anti-commutators of psi, that you have some sort of quantization condition that you will get this. Whereas if you had imposed canonical commutation relationships on psi, then you will not get this zero. And the details are in the details of the calculations are in the book by Schwartz. So I think that's pretty nice. Okay.
So that just shows that you need anti-commutation relations for half-limit spins.
Right. Yes. The causality puts a bound.
Yeah. And then how would you show like the similar arguments for integer spins?
Yes. Exactly. For integer spins, it's even easier because this could be the field, right? This was the field itself, right? So then, you're like, because the physical interpretation of this is that we are doing two simultaneous observations, right? And simultaneity means that you're on outside the light cone.
And when earlier, like Dan proved this for the expectation, at least the expectation of that on the vacuum was zero.
Sorry?
Earlier, Dan proved that the expectation of that in the vacuum was zero by like doing Lorentz transformations.
Okay.
I assume you can't do a similar thing here. Or?
I'll have to look at Dan's calculation more carefully to say that. Yeah. Okay, so number 3 is stability. So if you impose that your Hamiltonian is positive semi-definite, then that implies the spin statistics result, at least in 3 + 1 dimensions. So this is a sufficient condition. That is, if you just impose this, then the spin statistics result follows. But it is not necessary. So this is very important for, say, condensed matter systems. So in 3 + 1 dimensional condensed matter system, where we don't impose Lorentz invariance, because they're non-relativistic systems, we still have fermions quantized according to some anti-commutation relationships, and bosons, satisfy commutation relationships. And that comes from the fact that, we want the energy of these systems to be positive. Okay, so that's an important application, or important connection, I should say, okay? And has interesting consequences, say, for condensed matter systems. Okay, so enough waffle, and now let us quantize a free Dirac field. Okay, any questions so far? I mean, this is kind of vague, but I think there are lots of detail. There's a whole chapter dedicated to these nice topics in Matthew Schwartz's book, and the library has a couple of copies. So.
Promote psi to an operator. Exactly. Several lectures ago, we wrote psi as a ket.
Psi as a
spin.
Right. Yes. So so psi has many indices, and it's good to come back to this. Okay. So before this lecture, I was mostly concerned about psi being a classical object, right? So psi as a Dirac spinner, suppose psi is a Dirac spinner. Then it is a 4-component object, right? So I'm not hiding anything from you anymore now. Okay? So that means it's a 4-dimensional complex vector space. Because these guys, now, whenever there is, so that's what I meant by the ket. So when I wrote psi of x as a ket, S0, S1, S2, S3, I really meant this. Sorry, this is not how I presented it, right? S0 and S1, right? Because each of these can take, because if we write the dimension as 2k plus 2, for d equals to 4, we get 2 plus 2. That means k is, right, k is 1. So this was S0 and this was Sk, right? So each of these guys can take half or minus half. So how many possibilities are there? 4. So this guy has 4 components. That's what I mean by 4 components. So although I use the ket notation here, I did not mean it in a quantum mechanical sense. I meant it in a group theoretic sense. That whenever we have as physicists, whenever we have like some kind of vector space, a lot of times we denote that vector by a ket. It's a notational, it's an abuse of notation or an extension of notation. So, okay?
But are we to interpret it as a state when we're doing quantum?
No, we are not. No. This is a purely linear algebraic. We were building up from the algebra, we were building up this whole thing, right? So to argue that it had 4 components, that's why I was using kind of the group theory. I was using a language very similar to the angular momentum algebra that we use. Because, the angular momentum algebra is just a group theoretic thing. Quantum mechanics uses it. That doesn't mean that it's inherently, quantum. So here it's a classical field, but anyway, we can probably come back to this after class as well. Yes?
Are there any restrictions on the four components with regard, like?
They have to solve the Dirac equation.
Right.
Yeah. No, but in a general reference frame, general basis, there are no other. If they are complex, and they have to transform as a spinor, and there are solutions to the Dirac equation. Okay. Yes.
When you stated the spin statistics theorem, you stated in 3 plus 1D specifically. Right? Doesn't it hold in any dimensions?
So, as I said, in 2 plus 1 dimensions, it doesn't hold.
There will be other possibilities, but they won't have integer nor half integer spin. So
right.
The integer spin particles will still be boson, and the half integer will still.
Oh yeah, exactly, yeah. Yes. So I think that is the correct. Yeah, that is correct. Yes. So there could be non-integer, but what would their transformation property be? How do anyons transform classical anyons? Does anyone know? Under 2 plus 1 dimensional Lorentz group. Okay. Anyway, so that's a good question. So. Right, so recall that, so let us take when we quantize, we usually end up in the Schrodinger picture. I don't remember if I wrote it upstairs or downstairs. So I'm taking the wave function, which is the solution to the Dirac equation, at, say, t equals to 0. Right. And a similar one for the dagger. Now, this has some, this is the spinor index. The momentum conjugate to this is, as you know from classical mechanics, is defined like this. So that tells us it's given by, so if you look at the Dirac Lagrangian, this is what you get. So we are going to impose an anti-commutation relationship. So in other words, Yeah?
Your big S in the next line. That's a function of P, right?
Thank you. Also, I'm just going to restore just to remind you that there's a factor of h bar on the right-hand side of this equation. Okay? Why do I need the h bar? Just to kind of tell you that in the naive limit, naive classical limit, h bar going to 0, the psi and psi dagger anticommutes. Also, along with those anti-commutation relationships, we need to so this is just box comment. So we are not setting h bar equals to 0 for this lecture. But when you do a path integral, in the path integral, all the fields are classical, although the measure is just weird. And that's what gives the quantum effects in the path integral formulation. There, all the fermionic fields will anti-commute. So, so we also want to, for our quantum mechanical case, the commutator and the anti-commutator, anti-commutator of psi and psi with itself is 0. So that we also impose that. So for Fermi statistics to be imposed, those guys better lead to these relationships. And I'll stick to Dan's normalizations. So these two guys should be equivalent. So that commutation relationship should be equivalent to these two. Also, anti-commutation relationships. Also, the anti-commutator of B with C, B with C dagger, B dagger with C, B dagger with C dagger, they all vanish. Okay? So this is the essence of Fermi statistics. The fact that these guys anti-commute mean that if you create two particle states, the state will be antisymmetric under the exchange of particle 1 and particle 2, right? Okay. Although this is like one of the most boring things in the world, it is good to do these calculations once in your life. So I'm going to make you do that in the tutorial today, but I'm going to just sketch out one of the calculations myself, just to kind of, or is this something I should just skip? You guys are like, we don't care. Sorry? Okay. You can do it in a tutorial, right?
Yeah.
Good. Because, yes, right.
Can you just say why this limit is naive?
Because I don't want to get into trouble. I added the word naive because I don't want to get into trouble with quantum foundations people. Because for them, the classical limit is not something that is solved, which is true. It's not solved. And what is the classical limit? In some sense, there is no such thing as classical limit. I guess there is, yeah, when you think. But for example, the stability of particles, which we take for granted in classical physics, it's actually not true, right? You require quantum mechanics for stability and stuff like that. Anyway, that's just to kind of, be on the safe side of quantum foundations people. Yeah, I just didn't want Daniel back there to kind of give me a hard time. What is it? What do you mean? Okay, so like a page and a half calculation shows that the anti-commutation relationship that I imposed over there lead to these guys and vice versa. And to show that, you have to use all the wonderful, to prove these sort of identities, you have to use all the wonderful, spinner sort of algebra stuff that the linear algebraic relationships between U's and V's that I kind of flashed, you have to use a lot of those things. So it's good to do those calculations because then you have those things in your brain. Okay. Okay, one other comment about these guys, that in the limit where h bar goes to 0, the anti-commutating functions psi x and psi dagger of x, they're called Grassmann variables. So they're anti-commutating C functions. C stands for classical. And you can think of them as a linear combination of normal commuting functions on some orthogonal basis. And alpha n's are constant, which are Grassmann numbers. However, it does lead to some puzzles in classical physics, which we will not go into. Okay. So now we can ask what is the Hamiltonian for this system. So the Hamiltonian is probably the single most important operator. So at some point, I'm going to send you a link to the Psy song, the PI Blues song that Mark Wise wrote a few years ago. He adapted a song by, who is this? Johnny Cash's, Folsom Prison Blues into PI Prison Blues. And there's this immortal line in that song, is that my mama tell me don't play with Hamiltonians. When I was a child, my mama said, son, don't play with Hamiltonians. But I did a problem set in Reno just to kind of, Anyway, it's a great song, and I'm going to send it to you guys. It'll describe your life perfectly. Okay. So we do a Legendre transformation where we replace the generalized velocities by there's a sum over A, by the way. so this is now classical. We replace the generalized velocity by the generalized momentum, and this leads to an expression where I only runs over the spatial indices. Okay. So now you can use the Dirac equation. So now if you quantize it, you can use the Dirac equation for U, V, and those relationships that I wrote out about the completeness relationships to find that the quantum mechanical or the quantum field theoretic expression for this Hamiltonian is given by which is almost similar to what you got for the complex scalar field. Did you do the Hamiltonian for the complex scalar field? You just did it for the real, right? Or complex? Oh, you did the. Oh, then you have done it, of course. And I'm sure you remember all the details of it too. But the important thing is that when you worked out the Hamiltonian for the complex scalar field, you had a plus sign here. And now you have a minus sign. So you see that this is not in the correct order. So we can use the commutation relationship here, and then we get the same junk here, and then not junk, but stuff. And then we get the vacuum energy term as we got in the bosonic case with an important difference. So okay, so this is a very important expression for the Hamiltonian. So this is a positive definite number operator. This is a positive definite number operator. This counts the number of particles you have in the system. This counts the number of antiparticles you have in the system. We'll come back to their interpretation shortly. But this is the 0-point energy. But notice there's a minus sign here. There was a plus sign when we did the calculation for the scalar field. You might say, why are we worrying about this? This is the nice infinite term that we throw away anyway. But as mentioned earlier, is that this guy actually shows up in calculations involving relativity. So in curved space-time, this actually adds a new term to your action, and it acts as a cosmological constant. So as you may have heard, we live in a universe which has non-zero, but very small, but non-zero and positive cosmological constant. So the fact that this has a minus sign here is important when you consider theories, when you consider cosmology, right? And suppose you had a theory in which the number of bosons was exactly equal to the number of degrees of freedom of the fermions, then the 0-point energy would actually cancel out, right? And such theories are known as supersymmetric theories. And in supersymmetric theories, you do not have a vacuum energy. They're zero. Okay. So since we are not going to be so we are going to subtract that energy by saying that our Hamiltonian is going to be normal ordered. But remember how we define normal ordering, how Dan defined normal ordering is that you push inside the normal ordering sign, you push the annihilation operator on the right to the of the creation operators, right? That's how, but for fermions, when you do that, you have to actually, when you do one, you have to introduce a minus sign, okay? So normal ordering for Hamiltonian will involve anti-commutating rather than commutating. Otherwise, you will see that this sign will not change, and you will get a Hamiltonian which is not positive definite, and that is bad news for a free theory. Okay? So your energy would be unbounded from below. Okay? And there, so what I mean is, for this to work out, you have to define your normal ordering as, say, A, B dagger. So this is not normal ordered, minus of B dagger of A. And that is now normal order, so we can get rid of the normal ordering sign. Okay. So let's verify that this Hamiltonian does what it's supposed to do. That is, it gives you, it has the correct normalization. So, because the way that we have normalized our states and our operators, it's not obvious from the expression of the Hamiltonian that the units work out. So let's just do a quick calculation to make sure that that works out. A consistency check, if you like. The battery is running low. Okay, so let's consider one particle state. Say B dagger. So now, instead of writing B star and C star, I'm going to write daggers because now they're quantum mechanical operators acting on some Hilbert space. So this guy acting on the vacuum creates a one particle state which has momentum K and spin or polarization S. So now you apply the H on this guy. Then you can rewrite I'm just going to there was a factor of half here, and let's put an E of P, and then multiply by E of P. And then we had a sum over the spin, and inside there was B dagger R of P, B of R of P, and then there was another term which was C dagger of R of P, C of R of P, okay? And this whole thing was acting on B of S of K acting on the vacuum. Now, when these guys act on this, they all anti-commute. So this annihilation operator goes through this, just picks up a minus sign, and destroys the vacuum. So the second term does not contribute anything. On the first term, you can use the anti-commutation relationship between this guy and this guy, and then what happens is everything else until here remains the same. But over here you pick up 2 pi cubed delta of S of R delta 3 of P minus K. Anything else? Am I missing? Yeah. 2 times E of P, right? And then you do the integral over P using this delta function. You see the sum over R using this S. This 2EP cancels this 2EP, and as a result, you get E of K times So I know this was kind of a almost trivial calculation, but if you haven't seen this before, you have to do it. You have to check whether you have chosen all your normalization conditions to be consistent. That's what we have done. Okay. So what are the other interesting operators in this theory? Oh, by the way, in tomorrow's tutorial, there will be a problem about the classical limit. Not the classical limit, sorry. The non-relativistic limit. Sorry, I don't want to go into the classical limit. Okay, non-relativistic limit of the quantum field theory. Okay, so the other operator we like is Q. And remember, Q was, I think there was a minus sign. The zeroth component, which was psi dagger x of psi of x. So this is the classical expression. Now here, the integral is all over all space, but this guy, the conservation law, also implies that the charge is conserved locally as well. And so what I mean is that if you have some region in space, say sigma, then the integral over that region of the J0 component is also conserved. Now, we all know that charge is a Lorentz invariant quantity, and it So that means that this thing should also be Lorentz invariant. And one way of seeing this, I'll return in a few minutes how you can see that this is a Lorentz invariant quantity. So before we do that, okay, so if you do the same now, so if you now go to if you quantize and we compute the normal ordered expression for the charge, the total charge, we get something of this form. Well, we actually get this. Again, there is a very important minus sign here. So this is a positive definite operator. C dagger C is a positive definite operator. But because of the minus sign, Q is not a positive definite operator. Right? So any state, say, which has, say, C dagger acting on it, say, if you create a state like this, that's going to have positive eigenvalue. Q is going to have a positive. Its eigenvalue with respect to Q is going to be positive. Whereas if you, so you can call that a positron state. So if you have B dagger acting on the vacuum, that'll have negative charge, and that you can call an electron. So is that clear? Why this is not positive definite, and why you can interpret it as a charge operator, because it measures the difference between an antiparticle and a particle, between antiparticle numbers and particle numbers. Okay? Yeah.
I'm not clear about why Q is not positive.
Because there's a minus. Because this is a positive definite operator.
Yeah.
And so is this.
If you take the expectation value, you should get a positive.
Right. In any state. So the way so it's kind of a cheat, because the way we are creating our state is by our whole Hilbert space is by acting on the vacuum by B dagger and C dagger. Okay. So if you create any arbitrary state like that, and you calculate what the expectation value of B dagger B is or C dagger C is for those states, it'll either be 0 or positive. That's not very hard to see. And therefore, because of this minus sign, and well, that minus sign is kind of irrelevant because we could have defined it to be minus of this, it's not a positive definite operator. Okay. Yeah? Yeah, I'm coming to that now.
And the size, they're not spinors, right?
Sorry?
The size there in the integral, they are not spinors, right?
Yes, they're spinors, yeah.
I thought we have to form a scalar, we have to use the Dirac conjugate.
Yeah, of course. I'm coming to that. Yeah. So what Perseus is worried about is a scalar is this guy. And that is a Lorentz invariant object, right? And whereas what we have the integrand here is the 0th component of this guy. Okay. Now, this expression, the thing that is in here is essentially what your is basically what J0 is, up to some integral, measure. Okay, what I'm trying to say here is that you can think of the J0 is the particle density, or the number density of net charge, the density of positive charges minus minus negative charges, right? So when you do a Lorentz transformation, the density, of course, changes, because if you have a little box, you know, the number of particles inside the box is not changing, but you're boosting, say, in this direction, so this dimension changes, say it shrinks. Okay? So the density becomes higher by some factor gamma or something. But in this integral, there is still, you know, that direction, you know, dilates by the same amount. So those two things cancel out, and therefore this integral remains invariant. Lorentz invariant. Okay, to summarize, I should really say something. So Dirac initially wanted a first-order differential equation for electrons, and he found this current, conserved current, and he wanted to interpret as a probability current. The reason why Dirac wanted a first-order equation for his electron, a relativistic equation, was because Schrödinger's equation is first-order in time, and that's why the probability density that comes from Schrödinger's equation is positive definite. So you see that his interpretation is almost correct if there are no antiparticles, right? If there are no antiparticles, you can interpret, you know, the minus of this J current as a probability current. But as soon as there's antiparticle, you know, that interpretation goes out the window, right? So that's just a historical side note. So I think it's Dirac who said that this equation was smarter than him. Okay, so to summarize, you know, B dagger R of P, this creates a particle of, say, spin state R and momentum P, and CR of dagger of P creates an antiparticle and on the other hand, B and C they destroy particles, and they're known as annihilation operators. And why I'm emphasizing this at this point in the lecture is because these interpretations are crucial. They crucially depend on the expressions that we wrote for Q and H. Even though before we called them informally, you know, creation annihilation operator, but it's really after looking at the forms of Q and H that we can make these interpretations. Okay, in the remaining 20 minutes, let's work out what the propagators are. So before we work out the propagators, let's go back to that expression of psi of A as a quantum operator and rewrite it in a Heisenberg picture. So in the Heisenberg picture, psi now will depend, as an operator, will depend on space-time. And this will have the relativistic normalization. So I'm rewriting the same thing again, you would think, but what is important now is that this is now a 4-vector inner product. That's what I mean by the Heisenberg. Whereas, in the Schrodinger picture, that was just a three-dimensional inner product. And now this has a dagger here, and then V. And you will find in the literature, these guys are sometimes called this, and I might do the same. So this is the positive frequency part, which has in the exponential has the negative sign, which contains the annihilation operators. And the negative frequency part has the plus sign in the exponential and has the creation operator for the antiparticles. Right? So similarly, psi bar or psi dagger of x so this is just notation. So so this is basically going to have the annihilation operator for the antiparticle, and this will be have the creation operator of the particle. So this would be coming from here, and this would come from here. Anyway, okay, propagators. Yeah.
With your full vector P,
Yeah.
restricting the zero component to the mesh shell, right?
Yes, the energy. Yeah, that's good. Yeah, so here we have P mu. P mu is sorry, I should probably write this. P mu is E times P. So P dot x is P mu x mu, which is eta mu nu P mu x mu, which is EP times T minus P dot x. Okay. So propagators rhymes with alligators. Somebody asked the question. Well, it does, right? Why are you surprised? I'm just stating an obvious fact. In case you're, it's always good to have, know what rhymes with what. In case you're going to write the quantum field theory sonnet or something. In quantum information, there's this tradition where people write sonnets. Like, for example, there's the quantum error correcting sonnet that, who is this? Daniel Gottesman's supervisor, what's his name? Preskill wrote, right? And apparently he had lots of problem, finding something that would rhyme with Gottesman. You know. So I just want to tell you a little story about propagators. I think it may have been Dyson who told Feynman that when he was writing down these functions, these were Green's functions, because they are basically solutions to the wave equation with source, right? As you saw in Dan's tutorial and lectures, and Feynman refused to look them up. So, so I think earlier in the course somebody asked the question, why are we calling these Green's functions propagators? I think the answer to that is Feynman refused to look up Green's functions. Okay. Okay, so before we write down the Feynman propagator, let's revisit the causality argument that I gave at the beginning of the lecture. And the causality argument was that outside the light cone, this should vanish. And we can impose this either by computing, by imposing anti-commutation relationships or commutation relationships. But we can try to impose this, and it turns out that you can only impose it if you use anti-commutation relationships. In particular, outside the light cone, we would expect this to be true. You saw for the scalar field theory, you saw the commutator version of this, and you saw that outside the light cone, this actually does vanish. So now, if you take this expression, so these are now Heisenberg picture expressions, and you compute what the left-hand side of this, then you get this guy. Sorry, I've switched to Greek indices for spinors. I should really stick to my convention of doing Latin indices. Right, where you solve this function d, and and there's an AB. So this is a 4x4 matrix. You saw this function d before. So this is something for you to show by yourself. You know, your after dinner project. And right, and you saw in Dan's part of the course that this thing vanishes outside the light cone, right? And it's kind of very easy to show, because if you're outside the light cone, then x minus y squared is it's space-like. Therefore, you can always rotate to a reference frame where the time component is 0. And then by relabeling the integral in one of these guys, the p to minus p, you see that the two expressions are the same, and therefore they become 0. Okay? So the real work is to actually just show that this expression. Okay. So the fact that this is 0 outside the light count is a statement. Okay, sorry. It leads to the following definition of the Feynman propagator. So we define the Feynman propagator S of f to be, and this is a 4x4 matrix now. So I should use an AB for spinor index. And it's the vacuum expectation value of the time ordered product okay. And okay, let me write AB here, but let me tell you what I mean by this. What I mean by this is that if t x0 is greater than y0, then this is psi of a of x, psi bar of b of y. But if y0 is greater than x0, then this is minus yeah? Oh, yeah, sorry. I think these indices are correct. Yeah, I think so, yeah.
So when was it? Either of the cases?
Oh, sorry, yeah, I should write that down. If x0 is greater than y0, or if x0 is less than y0. Okay. But what's important here is the minus sign that we have to use. Yes?
And is that minus sign the reason why you're calling it like S rather than
Sorry?
Is this exactly the same Feynman propagator as what we do with the scalar field?
No.
So it's like, yeah,
It's got spinor stuff, things like that.
and so that's why you call it.
Yes, and this minus sign is motivated by the anti-commutator over there, and for the fact that the time right. Yeah, for the time ordering operator to be Lorentz invariant, we need this minus sign.
What exactly do the spinor indices mean here?
Oh, they just mean that you're taking the A and B take 4 values. So psi is actually a matrix. It's a column matrix, right? And psi bar is a row matrix. So the Feynman propagator is actually a 4x4 matrix in this case. We'll see that when we actually compute scattering cross sections and in amplitudes, it'll fit in nicely with it'll be sandwiched between spinors and stuff, so it'll have to be a 4x4 matrix. Ben? Okay. You're saying should be B here and A here? That you might be correct. Let me check that. Yeah. He's looking it up on the internet right now. Fine. Yeah?
I'm a little, I know that they're meaning different things, but I just, maybe a quick clarification. A and B here are taking 4 values. They're the 4 entries in the direct spinner, right? But R and S are only taking 2 values, right?
But yeah, exactly.
So what are R and S representing?
So, right, okay, good question. So, U of R of P, there are 2 of these guys.
Right.
So, U1, it's a column. Each of them are 4 component column. So, remember U of R of P for in a general, for a general momentum is given by sigma dot P psi of R, and here this is sigma bar dot P psi of R. Okay, where R are 2 component matrices which satisfy this. Okay.
So R and S then, those are not vector spinor indices. They're labels for 2 different spins.
Exactly. They correspond to spin states. So, this can be seen as has 2 solutions, spin up and spin down, right? Whereas this represent the spin properties of a Dirac particle, which is necessarily a 4-component object, right? Whereas on the other hand, if I look at what V is, let's write V here. So I guess the terminology is polarization used for, that's usually used for vector particles. It's called a spin, so they're kind of, when I say U of R, I mean the spin of a particle. When I say V of R, the R refers to the spin of an antiparticle, right? So V R of P, on the other hand, is sigma dot P minus sigma dot P. And there's a psi of R and psi of R. And the most general solution to this, it's a 2-component object, so you know what it is. You've seen it in quantum mechanics, I think. The state on the Bloch sphere, an arbitrary state on the Bloch sphere, can be given by 2 angles, theta and phi. So you can also, use that as the most general parameterization of these guys, right? But you can have 1, 0, 0, 1 as well. So. Okay, so Feynman propagator, which thing are we going to erase now? That. Okay, I'm going to take 5 more minutes because is that all right? Okay. Because that will give you enough time to have your coffee and cake before the next class. So let's look at the first case where x0 is greater than y0. So according to our definition, S of x, x minus y, so x0 is greater than y0. Oops, time's over. So if you use your, if you expand these guys out now, and in terms of this, and use the properties of the spinners, and the creation and annihilation operators, you get an expression like this. So I've kind of given you the final expression because I've integrated also over the zeroth component of my 4 vector p. But this integral doesn't mean much until I tell you how you're going to evaluate the pole of the integrand. And sorry, I think this is actually the general expression for t for both time ordering. And then the next step is to verify that this is actually does the job. So the prescription for doing the P0 integral is so you're on the P0 plane, and you have E of P and minus of E of P as your 2 poles of this guy. So which means that you can write this denominator as P squared as P0 squared minus 3P vector squared minus M squared. So this means this is P0 squared minus EP squared. So given a fixed value of 3p, this is how EP is defined, and that's the pole. Now, if x0 is greater than y0, then as Dan showed you, the way you take you go off to infinity and then you close it in the lower half plane. However, if x0 is greater than y0, is less than y0, then you close it in the upper half plane. Okay, I think this is a very important topic, and I'm not going to do justice to it in the remaining 1 minute. So let me just come back to this at the beginning of next lecture before we go off to Yukawa theory. Okay, and today there's a tutorial at 3:30. Okay, thank you. Yes, right.
Supersymmetry buys you an exact cancellation.
Yes.
So on that view, what is the origin of the actual value that we have?
Oh, that's like a Nobel Prize winning answer. I know the answer, but I'm going to tell you because you'll publish it and get the Nobel Prize before me. We don't know. The thing is that supersymmetry does not give you that value.
Right. I'm just saying if you take the view that supersymmetry is correct.
Right. Well, then you should get 0. But supersymmetry is broken in our world. So it has to be broken in such a way that it is consistent with our particle physics experiment and consistent with the value of the cosmological constant. As far as I know, there's only one proposal which works, which is consistent with these, which involves supersymmetry and is consistent with these two. But there's a catch. You have 2 large extra dimensions for that. 2 large extra dimensions that, in principle, we should be able to verify whether they exist or not in the near future. Sorry?
How large?
I think they lead to violation of Newton's constant to the micrometer scale or something. So I don't know exactly how large, but large enough that Newton's law get modified in a very small, in a almost microscopic, micrometer or millimeter, right? Or anyway, something like this. So, yeah. So, but apart from that, I don't know. I haven't heard of any supersymmetric theory that seems to do both. That because you have to break supersymmetry in such a way that it is consistent with the known particle physics, and then you have to also be able to predict the. So yeah, supersymmetry doesn't seem to be doing what it was supposed to do. Well, it does one thing very properly, which is to actually solve the hierarchy problem. But then experimentally, we should be seeing probably the particles which solve the hierarchy problem. Anyway, I can still talk about this, but let me just finish the class.